Okay, let's look at a very basic proof that involves proving that the three interior angles of a triangle sum to 180 degrees. You might have seen many different ways of doing this, but this is probably the most basic way. Let's start with a definition of parallel lines. There's a pair of parallel lines, as is shown by the arrows pointing to the right. Then we have a line passing through both parallel lines, and that is called the transversal. Now let's create a triangle using the transversal. Something like that. And we can mark in the interior angles, call them A, B and C. Now look at angle A. Is there another angle on the diagram that is the same magnitude as angle A? There is, at the top there, and they are called alternate angles. Similarly, for angle C, for the same reason, alternate angles. Now at the top we have angles A, B and C, and together they form half a circle. How many degrees is half a circle? That's right, 180 degrees. So what can we conclude? We can conclude that A plus B plus C has to equal 180 degrees. A very elegant, simple proof. Do you know the area for a triangle? It's a half base times height, isn't it? Why is there a half in front of the formula? Well, the reason is that a triangle's area is exactly half of the rectangle that circumscribes it. Let's look at the diagram for that. There's our triangle. We've got our base B and our height H. There's our circumscribing rectangle. What we are saying is that the area of the triangle is exactly half of the area of that rectangle. Can we prove that in an easy way? Well, the area of the triangle is a half base times height, half B times H. The area of the rectangle is B times H, in other words, length times width. So it's very obvious, isn't it? The area of the rectangle, B times H, is twice a half times B times H. In other words, twice the area of the triangle. Another straightforward proof. Have you seen this shape? It's called a trapezium. Do you know the formula for the area of a trapezium? Let's find out. How would you go about working out its area? One way is to divide it up into basic shapes. First of all, let's label some of the sides. A and B are the two parallel sides, and the width of the height of the trapezium is H. Now we can divide that trapezium shape into three basic shapes: a triangle T1, a rectangle, and another triangle T2. Let's work out the area of each of those three shapes. And just to help us, let's call the base of triangle T1 X and the base of triangle T2 Y. So the area of triangle T1 is a half base times height, in other words a half XH. The area of triangle 2 is a half YH, and the area of the rectangle is AH. Now we want the sum of those three areas. There it is, total area. Can we simplify that? We can take out a factor of a half and H, and that's what it would look like. Now, we can simplify it some more because X and Y are not part of the final formula. Can we express X plus Y in another way? X plus Y, if you think about it for a moment, is the same as B minus A, isn't it? So there's our formula, almost complete. And then if we just simplify what's in the brackets, we end up having that the area of the trapezium is a half bracket A plus B times H. Another well-known shape, a circle. We've all learnt the area for a circle, pi r squared, and of course the circumference of a circle is 2 pi r, which we also need to keep in mind. But let's show the formula for the area of a circle, pi r squared. Probably the way you have seen it done is in this way. We start with a circle and divide it up into equal sized sectors like that. There's our circle of radius r. And then we cut up the pieces and rearrange them. Half along the top and half along the bottom. And that shape, roughly, we think of as being a rectangle. Of course, the more pieces we use, the more it will look like a rectangle, won't it? There's our rectangle. So that means, as a rough and ready estimate, the area of the circle would be approximately the same as the area of the rectangle. But what's the area of the rectangle? Well, we know the area of a rectangle is length times width. So how long is that rectangle? Do you see it's made up of half a circle? And what's the length of half a circle? It's half the circumference, isn't it? The circumference of a circle, as I said just earlier, is 2 pi r. So half of that would be pi r. So the length of the rectangle is pi r. There we are. And the width is r, the radius, because, again, as a rough and ready estimate, the width is approximately the same as the radius of the circle. And now the area of a rectangle is length times width, which is pi r times r, which comes out to be pi r squared. So this is probably the way you've seen the proof before. But let's try something a bit more elegant or a bit different. So instead of using a rectangle in that way, let's use triangles. Look at that green triangle, which is an isosceles triangle. And the angle we're using, we will call theta. There's our triangle. So we have our isosceles triangle. Now, do you know the area for a triangle that is not a right angle triangle where we have the angle between the two sides, as you can see there? It is a half r squared sine theta. In other words, it's a half times the product of the two sides times the sine of the angle between them. Have you seen that formula before? Okay, so we have the area of one triangle. Now, if we have n triangles in our circle, then our angle theta becomes 2 pi, because 2 pi represents a complete circle, divided by n. So that means our formula now becomes, for n triangles, a half nr squared sine 2 pi over n. When the angle is small, we can approximate and say that the sine of the angle is approximately equal to the angle itself. So sine 2 pi over n is approximately the same as saying 2 pi over n. So that means our formula becomes a half nr squared times 2 pi over n, and then you'll see that the 2's cancel and the n's cancel, and we have pi r squared as before. Now, of course, this can only occur when we have an infinitely large number of triangles and where the angle, of course, then approaches 0. In other words, it's the limiting case. All right, let's finish with one more. Do you know the formula for the surface area of a sphere? It's 4 pi r squared, where r is the radius of the sphere. There is a straightforward way of deriving that formula by using integration. There's our sphere on the left. Think of it as consisting of an infinite number of circles added together. We know the circumference of a circle is 2 pi r, and here's how we can work it out. As a diagram, 2 pi r, the circumference of a circle, think of that as a line, a straight line of length 2 pi r, and we are summing all of the different lengths for different radii. Now, when we work out the infinite sum, it immediately implies anti-differentiation or integration if we actually want the area. So there's the start. We will integrate our function c equals 2 pi r between 0 and 2r, because the maximum width of the sphere is the diameter, isn't it? 2r. Now, anti-differentiating 2 pi r, it means you add 1 to the power of r and divide by the new power, and that gives us pi r squared, because the 2's will cancel. And then we substitute for R2 capital R, and then we substitute 0, like that. And when we simplify that by expanding the brackets, you will find that the surface area of a sphere becomes 4 pi r squared. That's probably the most challenging of the examples I have shown you. I hope you've appreciated some of the ways we can go about proving things. So the message is, when you come across a new formula or a theorem or a proof, investigate it and find out where it came from. Just don't assume that it is true. Until next time, bye-bye.